Hey, charming little young people. Today we will do revision of radioactivity. So we will see what is radioactivity, what are the important things in this, and this is very important for IGCSE and ICSE students. Okay, so we will just see what is radioactivity. Radioactivity. So if we define radioactivity, we can say that radioactivity is spontaneous and random. Spontaneous, these are two very important words. Spontaneous and random emissions from nucleus of an atom to make the atom stable. Okay, mostly this is for, basically this is for IGCSE, and also ICSE can have a look at it when we are doing this radioactivity. So here we see it is a spontaneous and random. So these are two very important words, spontaneous and random, and also from the nucleus of an atom. So what do we mean by the word random and what do we mean by the word spontaneous? So when we talk about the word spontaneous, spontaneous means that it happens on its own. We don't need to initiate the process. If we have, let us say, 1 kg of an radioactive substance, it starts the emission on itself. We don't need to initiate it, we don't need to heat it or do anything. Okay, and by the word random, we mean that the atoms which will decay cannot be determined. Out of these atoms, there are so many atoms. Even if I have 1 kg of an radioactive substance, I have like millions and billions of atoms. So maybe this one decays, or maybe this one decays, or maybe this one decays. There is no way of knowing it. And also it is a purely nuclear phenomenon. So it happens in the nucleus of an atom. It has nothing to do with the electrons. It is a purely nuclear phenomenon. Okay, and it does not depend on any outside factors like what is the temperature, no effect. What is the pressure, no effect. So no effect because it is purely a nuclear phenomenon. So it has no effect on the outside conditions have no effect on it. It is spontaneous and random. Now why does this happen? To know why does this happen, we will have to dig little deeper into structure of an atom. So when I say Xaz is an atom, here A is the atomic number or number of protons. Number of protons. Okay. I'm so sorry. If the Z here is atomic number or number of protons. Okay. Z is atomic number or number of protons. And A is known as atomic mass number. A is known as atomic mass number. And it is number of protons plus number of electrons. Number of protons plus number of electrons, or you can call it as number of nucleons. Okay, together the neutrons and protons are called nucleons. So we know that in this atom, this is the nucleus which has protons and neutrons. Together they will be called as nucleons. And we have electrons orbiting around it like this. Okay, so basically we have number of protons as Z. If anyone asks you how many protons are there in an atom, you will say that number of protons is Z. Protons is Z, and number of neutrons, because it is a nucleus phenomena, so we should know, will be obviously A minus Z. Because what was A? Neutrons, protons plus neutrons, and what was Z? Protons. So number of neutrons is A minus Z. Okay, so here if we calculate mass of nucleons, it should be number of protons into mass of each proton, mass of a proton, plus number of neutrons into mass of neutron, mass of a neutron. Okay, so I can write this as Z times mass of proton plus A minus Z times mass of neutrons, because Z is the number of protons and this we proved is number of neutrons. Now one would think that mass of nucleons will be equal to the mass of nucleus. This is what we think, but this is not the case. The case is that mass of the nucleons, this is nucleons, okay, and nucleus. This is nucleons and nucleus. Nucleons. Nucleus. Mass of nucleons. Nucleons is greater than mass of nucleus. So where did this mass disappear? Where did this mass disappear when the nucleons were forming the nucleus? So this mass, the difference between mass of nucleons and the mass of nucleus, mass of nucleons minus mass of nucleus, is called mass defect, delta M, mass defect. And this mass defect turns into binding energy. E is equal to delta mc square, Einstein's equation. And this is the binding energy which holds the nucleus together. This is the binding energy which holds the nucleus together. See, in nucleus, you have positively charged protons. They should all repel each other and the nucleus should like just, uh, fall apart. But this binding energy is holding all of them together. And in physics, we are more concerned with binding energy per unit nucleon. How much binding energy is there on one nucleon? But as the atom becomes higher and higher, binding energy per nucleon decreases. And as the binding energy per nucleon decreases, the nucleus becomes unstable. And everything in the world wants to attain stability. So the nucleus, which has become unstable, like higher atoms which have more neutrons, in the periodic table, you have the F block elements here. These are all radioactive elements. The lanthanides and actinide series, they are all very heavy. Okay, so they are unstable. So they exhibit radioactivity to become more stable. Now there are three types of radiations, three types of radioactive emission. First is alpha decay. So alpha decay, alpha is nothing but a helium nucleus. You take a helium atom has two protons, two neutrons, and two electrons. You get rid of the electrons. Okay. So it is just alpha. Alpha particles are nothing but, you can call them as double ionized helium atoms or helium nucleus. Alpha is helium nucleus or double ionized helium atom. Okay. And whenever an atom gives out an alpha particle, okay, we denote it like this, helium 24 or alpha 24. It changes. This X will change to some other thing. This will be known as the parent nuclei. This will be known as the daughter nuclei. Okay. It changes into something else and A will decrease by 4 because here we have 4, 2 protons and 2 neutrons, and Z will decrease by 2. The example of this is uranium 92 238. It gives out an alpha particle and gives out an alpha particle like this and becomes 90 and 234, which is nothing but thorium. Okay. This is alpha decay. In the beta decay, what happens is very interesting. In the beta decay, inside the nucleus, one nucleus turns into a proton, an electron, and an anti-neutrino. Now this just dissipates. This is just energy, so it dissipates into air. Okay, it dissipates. This remains in the nucleus because it's very heavy. Okay, you must remember that proton, mass of proton is 10,000 times mass of electron. So it is very heavy. But when this neutron splits, this neutron splits, proton remains in the nucleus, but electron is too light, so it just comes out. Okay, and we denoted, see, this does not have any any proton, but any neutron, but the proton number is decreasing by 1. The proton number is increasing by 1. And so if we write like this, X, A, Z, what happens here is we can denote it as, either you can denote it as electron 1 0, or you can denote it as beta minus 1 0. And this will also change. This A will not change because here, see, this is 0, correct? This will not change. And Z will increase by 1. And to balance this, we have written here -1. Okay. We have written here -1 to balance this because the total should again be Z only, na? Law of conservation of charges. And here this will, because this has not changed, it is A only. Now, why will this not change? So think about it. Let us say we had 20 protons and 20 neutrons. So total was 40. Correct. Now one neutron has changed and become a proton. So neutrons are 19, but proton has become 21. So total is still 40. Okay. So that is why the proton number increases by 1, but the atomic number remains unchanged. And in gamma radiation, gamma is a radiation. Okay. Okay. And what is beta then? Beta is a fast moving electron. Fast moving electron. In gamma radiation, if a atom nucleus gives out in gamma radiation, there is no change. It is the same thing. See, this is also the parent nuclei. This is also the parent nuclei. But here it was changing from X to Y. So in very short, if I have to say alpha, beta, gamma. So what is alpha? Helium nucleus. Helium nucleus. This is fast moving electron. Fast moving electron. And this is just an electromagnetic radiation. Electromagnetic radiation. Okay. So if an element gives out an alpha particle, you must remember, this is very important, its atomic number decreases by 2. Its atomic number decreases by 2 and mass number decreases by 4. And the nucleus changes into something else. If a nucleus gives out a beta particle, its atomic mass number remains unchanged, but atomic number increases by 1, or the proton number increases by 1. And if it is gamma radiation, there is no change. The parent nuclei X will remain as it is. If it is polonium, it will still be polonium. Okay. Now alpha out of this is the heaviest because it has 2 protons and 2 neutrons. Since it is heaviest, it is the slowest, and it is least penetrating and least harmful. Even paper could stop this. Okay. Least penetrating, least harmful. Now obviously this is lighter and it is faster. Its speed is close to speed of light. Okay, not equal to speed of light, close to speed of light. And it is more penetrating, more harmful. More penetrating and more harmful. That's why you keep it in lead box. Okay, you always use lead box for radioactivity. They absorb the radioactive emissions. And this has no mass. This actually has no mass because it is not a particle. It is a radiation, electromagnetic radiation. It is the fastest because light is also electromagnetic radiation. So its speed is equal to speed of light. This is light actually. Spectrum, we had gamma radiations in spectrum. most penetrating, most harmful, most penetrating and most harmful. Also, alpha is the most ionizing. What do I mean by the word ionizing? See, when this alpha particles goes in a medium, it when it meets a gas atom, it collides with the gas electron and knocks it out. So the gas atom has now become an ion because it has lost one electron and gained a positive charge. So because it is slowest and heaviest, it suffers maximum number of collisions and it is most ionizing. And obviously beta will be less ionizing and gamma will be the least ionizing. Most ionizing, less ionizing, and least ionizing. Okay. And also this is positively charged because it has two protons. This is negatively charged because it is fast moving electron, and this has no charge. So it is deflected towards the positive, towards negative. In electric field, deflected towards negative. This is deflected to positive. And this is not deflected when we are talking about electric fields. EF means electric fields, okay? And in magnetic field also, gamma will not be deflected. Gamma in magnetic field. MF is magnetic field here, okay? Don't think something else. In MF, not deflected. And these two are deflected in magnetic field. This is also deflected in magnetic field. And the direction is given by Fleming's left-hand rule. Fleming's left-hand rule. You remember the left-hand rule? Thumb gives the direction of the force. The index finger gives the direction of the magnetic field. And the second finger gives the direction of the current. But use your left hand. Only fools use the right hand, okay? For this thing. And one more thing to remember, that conventional current, if your beta particle is going like this, conventional current goes like this. They are oppositely directed. Okay, remember this for Fleming's left hand rule. If beta particle is going this, you take current in this direction. Okay. And for this one alpha, the current and alpha have same directions. Okay. Now there is something called as half-life. Now what is half-life? So if I have like 300, if there is 300 activity, 300 is the activity of the radioactive substance. In how much time it reduces to 1500. So let us say it reduces in 2 days. So further 2 days it will become 750. Further 2 days it will become 325. So it will keep on decreasing by factor of 2. It will not become 3000 to 1500 and then to 0. It will become half of this. Okay. This is known as a half-life or half-life period. Okay, so that's easy. In how much time this is getting half. Also remember, if they have already given you the background radiations, let us say they say that 270 is the activity. Okay, and let us say they say that 18 is background radiation. Okay, and then they say that you find out in how much time it has, like come down to half of this. But let us take easier numbers. Let us say they say that this is 250 and 50 is the background radiation, and in how much time it is becoming, let us say they want to know in how many days it's becoming 50, and they say that the half-life is let us say 10 days. Okay, half-life is 10 days. So you remember, it will not become 50. They will say in how many days it becomes 60 because that is background radiation. Okay. So first from this 250, so 50 is the background radiation, and we have to check in how much time it becomes, let us say in how much time it becomes 100. That is what they are asking. Okay, let us just change this question. So from 250, first you remove 50, this becomes 200. Then you do half of it, it becomes 100. Then you do again half of it, it becomes 100. Then you add the background radiation. So you have 10 days here and 10 days here, you get 20 days. So always you will have to correct it for the background radiation. Okay. You will always have to correct it for the background radiation. Apart from this, we just have nuclear fission and nuclear fusion. So in nuclear fission, you have a big heavy atom. This is heavy nucleus. You bombard it with something, you strike it with something, and it splits up into two lighter nuclei. Okay. But the mass of the heavy nucleus is greater. Mass of the heavy nucleus is greater than the mass of the two lighter nuclei combined. So again, there is mass defect, heavy minus the mass of the two lighter ones. It may be 2 or more than 2. This is equal to delta M, and this delta M becomes energy. This is what we used in, I mean, not we, this is what is used in atomic blasts, because in that we use uranium. So we strike it with one neutron and it gives energy, and it also produces 3 more neutrons. So it's a chain reaction. These 3 will produce 3 more. So it's a GP. Okay, geometric progression. It goes on increasing. And then second is nuclear fusion, in which two lighter nuclei combine to form one heavy nucleus. Okay, but here again the problem is that the mass of the lighter nuclei is greater than the mass of the heavy nucleus. So again we get mass defect, which comes out as energy. Okay. This again becomes energy. But you remember that nuclear fusion, this is very important. Nuclear fusion requires very high temperature and also pressure. High temperature and pressure is required. So it is not possible on Earth. It is the fuel of stars. They ask this in MCQs. It is fuel of stars. Okay. And it produces lots of more energy than nuclear fission. No one has achieved nuclear fusion on Earth. I think you can do it. Do the experiments. Okay. So thank you very much. I hope you study good for your exam, and I'll be putting up more videos. Thank you.